This is Programming Chapter 2. We're going to look at native data types, memory addressing, and the CPU. Identifiers are simply what we call pieces of code and data. Identifiers must start with a letter followed by any number of alphanumerics or underscore. Identifiers make code readable, so instead of saying a piece of data is located at memory address 19864, we can just refer to it as something like line number. If you add more code, the compiler can automatically adjust this number rather than having you do it manually. Because if you add more lines of code, that's going to push this address up higher. It's also best practice to follow naming conventions. These vary depending on the language, and using conventions make it easier for you to read other people's code and for other people to read your code. Because compilers are pretty quick and we have a lot of memory, there are autocomplete features in IDEs. So there's no excuse for using cryptic identifiers such as LN instead of line number. For multi-word identifiers, we capitalize the start of new words or use underscores. So here we have line, capital N, number. Here we can just use line, underscore, number. Finally, you can't use identifiers that are reserved words, such as if, for, and switch. It's also generally best to avoid identifiers that are part of standard libraries. At this point, you can't avoid it because you don't know all the functions in the standard libraries. But later on, you'll be expected to avoid those identifiers. Note that identifiers are case sensitive. And when you have an error with an identifier, just make sure the cases match. So, for instance, here I have print capital F. Here is print lowercase f, and this is correct. This is highlighted with red, that's an error. If you hover over this, you can see that it says printf is undefined. So whenever you get an undefined, you need to check that it's spelled correctly and has the proper case. Okay, so your first task is to email me a link with the naming conventions and the reserved words for the language that you have chosen to work on. So for Java, look up the naming conventions and the reserved words. And for Objective-C, same thing. Look up the naming conventions and reserved words. And what you need to do is just email me the link to the web page that has this. Also, just send me 4 reserved words in the email as well. Okay, it doesn't matter which language you choose. The basic native data types are integers, floating point numbers, and characters. The computer treats everything as numbers. And I'll go over that in a bit. The basic unit of memory is a byte, and that typically has 8 bits. A bit is simply a 0 or a 1. Its value depends on the bit position. So if we're working with decimal numbers, say 1952, okay, the 2 is in the 1's place, so it's worth 2. The 5 is in the 10's place, so it's worth 50. The 9 is in the 100's place, so it's worth 900, and the 1 is in the 1000's place, so that's worth 1000. So this is working off powers of 10. Binary works off powers of 2s. So, an 8-bit will hold integer values between 0 and 255, or negative 128 to 127. If we have 3 decimal places, the largest number we can hold is 9999. So that's 10 to the power of 3 minus 1. For a byte, we have 2 to the power of 8 minus 1. So that's 255. This one is 1000 minus 1, that's 999. for negative numbers, we just use the high bit as the negative sign. So that's why we have half the value. Half of 255 is roughly 128. An int type is generally defined as the data bus size. We have an address bus on a computer and we have a data bus on a computer. If we have a 32-bit processor, that's 4 bytes. And it can hold values up to 4 billion and some odd digits. If you have a 64-bit processor, that's 8 bytes. And that's very large. That's 1.85 times 10 to the 19. The first Apple, Commodore, and Atari computers were 8-bit processors. So the largest value was 255. The first IBM PC was only a 16-bit computer. So that held numbers up to 65536. Now the address bus can have a different number of bits than the data bus. So the data bus tells you how big the numbers can be. The address bus tells you how much memory the CPU can access. And currently, we don't have any computers that hold 1 times 10 to the 19 bytes of RAM. So typically, the address bus is smaller than the data bus. And 8-bit processors of way back when had 16-bit addresses, which means you can have 64K of RAM, or this much. Choosing data and address bus sizes is a matter of what's practical. And what's practical is determined by how many wires you want, because each bit has to be physically wired from the CPU to the memory or the I/O, which is hardware. Let's look at how binary numbers are represented. This is the first digit, so it's 2 to the power of 0, which is 1. This is the next digit, which is 2 to the power of 1, and that's 2. 2 to the power of 2 is 4, that's the next digit. This is the 1's place, 2's place, 4's place, 8's place, 16's place, 32's place, 64's place, and 128's place. Okay, so we have all those numbers. When it's a 1, we add that place value. When it's a 0, we skip that place value. So this is 128 plus 32 plus 16 plus 2 plus 1, which are the values here. And you add them all up. This number represents 155 in decimal. Now, converting to hexadecimal is actually easier. So what we do is we group 4 digits. That's the 1's place. And hexadecimal means 16. So this is 16 to the power of 0. This is 16 to the power of 1. So whatever digit we have, that's multiplied by 16. Whatever digit we have here, we multiply by 1. Okay, so the last 4 digits is 1011. So 2 to the power of 0, 2 to the power of 1, and 2 to the power of 3. Or you can look at the chart. This is B. So our last digit is B. Our first digit is the first 4 binary digits. And 0, 0, 1. 2 to the power of 0, 2 to the power of 3. Or you can look up, this is a 9. So our full hexadecimal number is 9B. This number is obviously a hexadecimal number because it has letters. If it was 99, you would have to put an H on the bottom to specify that it's hexadecimal. Otherwise, people might confuse it for a decimal value. Another way to represent hexadecimals is with a $sign. And this is left over from people who like to do assembly language programming. Okay, so your next task is to email the decimal and hexadecimal value of this binary value. So, characters. Characters are numbers. And for ASCII characters, this is an 8-bit way to represent characters. The real printable characters start at 32 and go up to 126. 65 represents a capital A, 97 represents a lowercase a. This is much more compact than storing a bitmap for a capital A. And once you store a bitmap for a capital A, it's stuck in that one font. Here, if you just use 65 to represent A, you can print it in any font you like. The more modern way of storing characters is with Unicodes. Unicodes can take more than 1 byte, but it handles many different languages. We're not going to worry about Unicodes right now. And the reason why I'm telling you what these ASCII codes are is for debugging your program. If you're looking at a string in memory, you might only get numbers. And if it's not displaying the text, you need to be able to convert the numbers into text. Now, the hardest native data type to understand is floats. Okay, they're easy to use. You understand floating point numbers because they have decimals. It's also scientific notation, but they're easy to misuse, and we'll cover this later. Now, scientific notation in binary, it's somewhat like scientific notation, but it's slightly different. And most computers will follow the IEEE 754 convention for floating point. Now, I'm not asking you to understand this format because it's difficult. It doesn't make sense when you look at it, but that's what's used. What you need to know is how much precision does a float have and how much precision does a double have? Because if your application requires a lot of decimal places, you'll want to use a double. If it doesn't, you can use a float. Remember, a double will take up twice as much memory as a float, but you have less rounding errors with doubles. The more times you carry over calculations, you keep losing precision. And what I'd like you to do is email me a link to a description of IEEE 754. And you also need to tell me how many significant digits in decimal are there in a 32-bit float and in a 64-bit float. So this would be a float, this would be a double. The last native data type is a Boolean. And the number of bits a Boolean uses depends on the compiler and the language. But what a Boolean does is it just holds a true value or a false value. And most languages simply treat a non-zero value as true and a zero value as false. And we'll cover more on Booleans later. That's it for part 1 of chapter 2. Please do some exercises and then continue with part 2 of chapter 2 video. And that completes this lesson.